Hypothalamus Artificial Intelligence, HI, and Research Center for Advanced Decision Technologies, RCADT, a division of HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Present the conference. Optimization under uncertainty and risk management. The material of conference was organized by the engineer Jesus Velasquez Bermudez, Ph.D. Enterprise Risk Management, ERM. Holistic Risk Management, Strategic Risk Management, Enterprise Risk Management. Whatever you choose to call it, risk management is undergoing a fundamental shift within leading organizations, which are moving away from the individual departmental approach, silo by silo, to manage risk more holistically and coherently. Against the Gods, the remarkable story of risk, the measure of our ignorance. According to Peter Bernstein, in his book, Against the Gods, the remarkable story of risk. The revolutionary idea that defines the boundary between modern times and the past is the mastery of risk, the notion that the future is more than a whim of the gods and that men and women are not passive before nature. The essence of risk management lies in maximizing the areas where we have some control over the outcome while minimizing the areas where we have absolutely no control over the outcome and the linkage between effect and cause is hidden from us. Optimization under uncertainty and risk management. Framework. Optimization under uncertainty is integrated by: first, robust optimization when the parameters of the model are characterized based on variation ranges, and the objective of the model is to produce the best solution considering the worst situation for the occurrence of the parameters. Second, stochastic optimization when model parameters are characterized probabilistically and therefore all results can be associated with empirical probability distribution functions that depend on the risk management policy. The stochastic optimization process. It is composed of 3 stages. Identification of the stochastic process model, implementation of a synthetic scenario generator, and design and implementation optimization stochastic model for decision support. Stochastic optimization implies the definition of the decision-making process, definition of the uncertainty dimensions and the stochastic processes associated with parameters, the risk management policy, and the approach to use for the computational solution. Stochastic optimization implies the definition of the decision-making process, definition of the uncertainty dimensions and the stochastic processes associated with parameters, the risk management policy, and the approach to use for the computational solution. There are multiple decision criteria, objective functions, that can be integrated into models which are associated with the risk management policy and risk position, prone or adverse, of the decision maker. Scientific, financial and operational, risk management is the true benefit provided by stochastic optimization models. The complexity of this problem lies in its bi-criterion nature. Maximizing the expected revenue and minimizing the risk assumed in decisions under uncertainty. This is summarized in the Pareto curve risk versus expected revenue, which is the final information produced by mathematical models to support decision-making. Rockefeller and Yuryasev, Scientific Risk Control. Since the end of the past century, the mathematical formulations to control the CAIR and mathematical programming models were developed. Rockefeller and Yuryasev, 2002, Conditional Value at Risk for General Loss Distributions. These methodologies, for the scientific financial risk management, have been included in high-power models to control/manage financial risks and operational risks. The value at risk, VAR, is associated with a mathematically defined level of probability, by which the probability of it being exceeded is equal to a reference parametric probability. The conditional value at risk, CAIR, also known as mean excess loss, is defined as the expected cost conditioned in that the cost exceeds the value at risk, VAR. Risk arises in the probability concentration and a tail of the probability distribution function. If the risk comes from a high cost, it is reflected in exceeding a high limit of probability. If it comes from low income, the risk arises from not exceeding a low probability. CAIR is commonly used in stochastic optimization models when the goal is to minimize or limit VAR. At least 2 types of risks must be faced, financial and operational. Normally, financial risks are associated with the long term, however, there are short-term cases, such as cash flow risk. Operational risks are more associated with the short term, as is the risk of scarcity or abundance of water resources. However, there are also medium or long-term risks, such as a social protest or a similar event. Part of the success of enterprise risk management is the comprehensive management of the company's risks. An enterprise risk management strategy must differentiate risk control policies in the same model. In the short term, operational risks are controlled, and in the long term, financial risks. An example is the case of a water resources operator, who in the short term must worry about the scarcity or abundance of the resource, and in the long run, he must worry about the financial stability of the company. The following cases summarize the alternatives that the decision maker should analyze, and the impact of his or her decisions. Traditional approach. Minimize expected cost by ignoring risk. This approach will lead the system to rational maximum risk positions. It is a risk-prone position, and the risk of the decision is fixed by the model, not by the decision maker. Inclusion of a cost-care constraint. Minimize expected cost by restricting risk. This approach will lead the system directly into rational risk positions from a financial point of view and, indirectly, from an operational point of view. The financial risk position is a decision of the decision maker. Inclusion of a care constraint. Minimize the expected cost by directly restricting the risk of rationing and indirect financial risks. The operational risk position is a decision of the decision maker. Inclusion of a restriction for short-term care. Minimize expected cost by directly constraining short-term risk. In long-term models, the focus is on controlling short-term operational risk, as it is the real problem that needs to be solved. It makes no sense to control operational risk in the long term. Minimize care in the short term, restricting expected costs of the system. It would be the most effective from the standpoint of minimizing care violations. The cost level is necessary to avoid solutions associated with higher than reasonable operating costs. Like any by-criteria problem, solving the risk management problem is not achieved with a simple run of a mathematical model. The decision-making process requires to develop knowledge that allows the decision makers to rationalize its decision. For this purpose, the efficient, Pareto, frontier risk versus utility must be built. Once it is built, the decision maker must select its risk position by choosing the point on the curve at which it wants to set the decision. The Pareto curves of the VAR and the CARE have been developed by parametrically solving several cases, which allows comparing risk and revenue. In this case, empirical distributions are included for risk control through the value at risk and the conditional value at risk. The number of scenarios determines the fit of the empirical distribution function resulting from stochastic optimization models. Therefore, the power of the computer becomes an important parameter. The graph presents the empirical distribution obtained using GSDDP without risk management. It corresponds to the conventional expansion model, which produces the riskiest distribution of income, because the range covered by the empirical solution is the largest. GSDDP accepts the criterion of statistical convergence, based on the accuracy of the estimator with respect to the value of the objective function, or another random variable of the model. The standard error estimator, C, is calculated during execution, and its calculation is used to determine convergence. Risk management aims to control the extremes of the probability distribution function, since exceeding them or not exceeding them generates risk. For example, if the top end is reduced to the red line, there will be less risk of high costs. Because of the multi-criteria nature of risk and expected value, risk management involves sacrificing revenue for risk. In this case, higher costs must be assumed to control the risk. This amount is a risk premium that must be paid. The graph presents the results of using GSDDP with risk management. The range covered by the empirical solution is shorter. Given the edge asymmetry associated with risk, the solution's statistics change. Risk management involves increasing average costs of $387.0 to $392.84, in exchange for reducing the range from $178.72 to $151.94. Stochastic programming is related to the computational implementation of stochastic optimization models. One of the characteristics of stochastic programming models based on scenarios is that they provide probabilistic information to all the variables in the model, primal and dual. This allows build empirical probability distribution curves on which we can apply restrictions in the modeling or turn them into objective of optimization modeling. This is the way to include scientific risk management in stochastic programming models. The main statistics for all the variables of the mathematical model and for variables derived from these solutions can be calculated from the empirical distribution. These statistics may be probability, expected value, variance, standard deviation, the maximum, or the minimum, value, the range, var, value at risk, and CAIR, conditional value at risk. Therefore, it is possible to condition the mathematical model so that it complies with certain values of statistics reflecting the decision-maker risk position. The selection of statistics to consider can depend on the mathematical complications involving their calculation, such as the expected value, the maximum, or the minimum, value, the range. The CAIR and the var involve linear models on continuous variables. The probability implies linear models on binary variables. The standard deviation and variance involve quadratic models on continuous variables. Another aspect to consider is the handling of the tails of the probability distribution because the risks are associated with the impact of extreme events. In these cases, the var and the CAIR are aimed at controlling the behavior of extreme events, while the other statistics make emphasis on the mean of the distribution. For this reason, the most convenient is controlling the CAIR that implicitly controls the var. Stochastic programming, synthetic stochastic process. The modeling of random events in optimization models is supported by, we don't know what will happen, but we know what can happen. Random events are modeled based on scenarios, which are assigned to probabilities of occurrence. The synthetic generation of the stochastic process aims to generate the data that will be used as input to generate the decision tree scenarios. Exogenous random parameters, or uncertainty dimensions, that are considered to be part of the stochastic process, must be generated. In this process, it is important to respect what has been observed in history. The tradition is to use methodologies that consider history as true, deterministic, and that from today generate the necessary number of multivariate synthetic series. More mathematically advanced methodologies, which consider history as a random variable and perform a synthetic generation of the past, and from there generate the synthetic series of the future, are more consistent with hybrid artificial intelligence. An example is to use state estimation methodologies, such as the Kalman filter. Stochastic programming, decision trees. Stochastic programming, synthetic stochastic process. The modeling of random events in optimization models is supported by, we don't know what will happen, but we know what can happen. Random events are modeled based on scenarios, which are assigned to probabilities of occurrence. The most well-known decision-making process is the so-called two-stage stochastic optimization. In this case there are two stages. Here and now, which corresponds to the first period for which decisions will be made, and the future, which has a single period or second stage, in which the expected cost of multiple scenarios is evaluated, conditioned by the decisions of the first stage. Multi-stage stochastic programming is a more complex process in which there is multi-stage decision-making, which can be interpreted as a concatenation of multiple two-stage trees. At the beginning of the first stage, t equals 1, the deterministic decision x1 is made. After x1 there is an realization of the stochastic process, w11. Now, a new decision has to be made, x21. Later, the w21 scenario will occur, and then the decision x31 must be made and so on until the last stage, t equals t, is reached. Multi-stage stochastic programming involves evaluating the entire mix of scenarios and periods. Mathematical methods will be responsible for facilitating and speeding up the process. Split variables methodology facilitates the implementation of decision trees. It consists of parallelizing the decision trees by making copies of the variables for all scenarios. As a result, there are as many parallel problems as there are scenarios. Non-anticipative constraints formulation. This constraint ensures that the values of the non-anticipative variables are the same for all internal scenarios that belong to the decision tree. In solution approaches that use large-scale methodologies, such as Bender's theory or Lagrangian relaxation, these constraints are part of the coordinating problem. A structure of two levels is established to solve the problem. The first level, the coordinator, is the problem in terms of non-anticipative constraints. The second level is a subproblem for each scenario that generates dual variables for the coordinator. The solution is obtained by exchanging information between the coordinator and the subproblem. The coordinator proposes a value for all scenarios, until all non-anticipatory constraints are equal. At the end of the process, the same result is obtained as the fully branched process. Stochastic programming can use simple methodologies, based on solving a monolithic deterministic problem equivalent to the stochastic model, or employ large-scale methodologies such as Bender's theory, Lagrangian relaxation, Dantzig-Wolff decomposition, column generation, and/or disjunctive programming. These methodologies can be combined using cross-decomposition concepts to implement parallel and/or distributed optimization. The Chapter 2-4, Dynamic and Stochastic Bender's Theory of the book. Mathematical Programming 4.0 for Industry 4.0 Cyber-Physical Systems. Present more information on this topic. Digital Industrial Revolutions. Today, the evolution of industrial revolutions is conceived as Industry 6.0 is completely changing the mathematical modeling of artificial intelligence. Now we can talk about orchestration of swarms of cognitive robots, and living industrial ecosystems. These two terms are new to most people, including scientists, even though they date back at least 15 years. Industry 4.0 is a consequence of the invention of the digital computer and digital automation. Its origin may be in 2011, and the result is digitalization and interconnectivity, smart factories, that is, cyber-physical systems. Industry 5.0, the first mentions date back to 2015, is humanization and close collaboration between people and cyber-physical cognitive robots based on artificial intelligence. The transition from Industry 4.0 to Industry 5.0 represents a paradigm shift. We move from an approach focused exclusively on technological efficiency to one that prioritizes human value, sustainability, and resilience. While Industry 4.0 sought to interconnect machines so that they could make autonomous decisions, Industry 5.0 seeks to make these machines work with people to enhance their creativity and well-being. Formally introduced by the European Commission in 2021, this revolution does not replace the previous one, but complements it under three fundamental concepts. Human centrism: technology should serve people, not the other way around. It focuses on improving the health, safety, and job satisfaction of workers. Sustainability prioritizes circular processes that reuse resources, reduce environmental impact, and respect the planet's limits. And resilience, the industry's ability to withstand and adapt quickly to global crises, such as pandemics or supply chain disruptions. Industry 6.0 currently has no date, as it is considered a visionary and conceptual phase that is still being defined, but which is based on intensive artificial intelligence. Total autonomy, biological symbiosis and industrial systems that function as living organisms. There are already examples of this situation, as is the case with smart grids and the Internet of Energy. Industry 6.0 focuses on the total symbiosis between humans, machines and biological systems to create living, regenerative and deeply ethical industrial ecosystems. Unlike its predecessors, it does not seek only efficiency or collaboration, but an integration where technology self-organizes and evolves along with society. The fundamental pillars are integration of mathematics and artificial intelligence, to produce artificial general intelligence, AGI, with the ability to understand, learn and apply knowledge in any intellectual task, in the same way, or even better than a human being. Human-machine biology symbiosis, fusion of human intuition, advanced artificial intelligence, and biological systems, such as self-healing materials or neurocognitive interfaces, Cognitive and proactive autonomy, transition from predictive maintenance to self-regulation and regeneration. Systems not only detect faults but are reconfigured to avoid them altogether. Regenerative sustainability, beyond reducing environmental damage, systems are designed to actively restore and enhance ecosystems through real-time circular economies, and ethical and conscious governance. AI incorporates moral reasoning and transparency, ensuring that autonomous decisions are aligned with human values and planetary well-being. The technologies related to Industry 6.0 are mathematical modeling, translation of real-world problems into a mathematical language, such as formulas, equations, or graphs, to understand, analyze, and predict behaviors of complex systems. Generative AI and AGI, co-creation of workflows and autonomous design of products based on abstract objectives. Quantum computing, massive data processing for optimization of ultra-complex supply chains and molecular simulations. Human digital twins, HDT, virtual replicas that simulate not only physical processes, but also emotional and cognitive dynamics of workers. Internet of Everything, I/O, and 6G, ubiquitous and ultra-low latency connectivity that enables the orchestration of swarms of cognitive robots and devices on a global and even spatial scale. Industry 6.0. A swarm of artificial intelligence algorithms, that is the orchestration of swarms of cognitive robots on a global scale. One aspect that becomes fundamental is the lives of professional people. Although professional development normally evolves to its maximum level at the end of university, however, it is common for professionals to lose knowledge during the exercise of their work and reach low levels of useful scientific knowledge. In the example, after high knowledge developed at the university, the actual exercise is limited to Excel, which is fundamentally arithmetic. This is another barrier that must be overcome. Now GPT is the intelligent, and super-fast, consultation of what is recorded on the internet, which limits many professionals to this knowledge. The difference between a scientific life and a real and ordinary life generate a big chasm, not a gap. In 1962 J. F. Benders published his theory oriented to optimization of large-scale problems. The fundamental idea is the partition of a problem into two sub-problems of reduced complexity based on the division of the variables like coordination variables and subordinate variables. The solution of the original problem is obtained by the coordinated solution of two complementary subproblems. The coordinator linked to the coordination variables, and the subproblem linked to subordinate variables. The subproblem provides information to the coordinator by the dual variables associated with its constraints. The coordinator takes the information from the primary level and incorporates it in the form of hyperplanes, Benders cuts, limiting the feasibility region for the optimal solution of the coordination variables. Benders cuts represent the cost of subordinate variables as a function of the coordination variables. The algorithm defined by Benders is convergent and solves the original problem through the solution of the coordinator problem, applies only to linear subproblems. Variations and improvements of the theory have extended its applicability to any type of problem. Lagrangian relaxation. Lagrangian relaxation is a mathematical technique used to solve complex problems of constrained optimization, simplifying them into relaxed versions that are easier to solve. It is especially effective for combinatorial optimization problems where a few hard constraints make the original problem computationally intractable. The method follows a divide-and-conquer philosophy. The steps to follow are: identify difficult constraints. Constraints are divided into two groups: easy constraints that can be resolved quickly, and hard constraints, lateral constraints that complicate the structure. Dualize with penalties. Hard constraints are removed from the constraint set and moved to the target function. Lagrange multipliers. Each relaxed restriction is multiplied by the Lagrange multiplier, which acts as a penalty for violating the restriction. The process to follow is: relaxed problem. For any fixed set of multipliers, solving the relaxed problem is usually easy. Quote generation. The solution to the relaxed problem provides a limit to the optimal value of the original problem, a lower limit for minimization, an upper limit for maximization. Lagrangian dual: to find the best possible bound, we solve a secondary optimization problem, the Lagrangian dual, which seeks to maximize the lower bound, or minimize the upper bound, by iteratively adjusting the multipliers. Updating multipliers: the subgradient method is often used to update multipliers, moving them in a direction that penalizes current constraint violations. It can also work with cutting planes. To model Lagrangian relaxation, LR, two questions must be decided. First, what constraints to relax to define the subproblems, and second, the strategy for updating the Lagrange multipliers. The objective function, together with the local min constraints, define the upper Lagrange bound problem. By relaxing these constraints, the problem can be separated into a subproblem for each cluster. The stochastic optimization problem uses a monolithic model that is traditionally solved by large-scale optimization techniques, Bender's partition and Lagrangian relaxation. The master problem can be associated with the company's board of directors. Each subproblem is associated with a scenario of the same system. Each scenario is randomly characterized to give rise to a probability distribution function. This problem can be solved in parallel, but it remains monolithic. An alternative to Bender's partition is to use Lagrangian relaxation, such as Bender's. The problem of Lagrangian relaxation must be broken down into 4 problems. Master problem, in charge of coordinating the subproblems, and 3 subproblems, 1 for each entity of the system. To solve the problem, a conversation is established between the master problem and the subproblems. The coordinating problem sets values of the dual variables, marginal costs, and the subproblems return information based on the primal variables. LR worked in the non-feasible zone of the primal variables, and in the feasible zone of the dual problem. In this case, Lagrange theory indicates that there is only one Lagrange multiplier and, therefore, it must be equal in all subproblems. The convergence of the integrated problem is achieved when in 2 consecutive iterations, the value of the Lagrange multipliers remains constant. The image presents the use of Lagrangian relaxation to solve the smart grid problem. Each subproblem corresponds to a smart grid, and the master problem is equivalent to the smart grid control center. The relaxed restrictions on all smart grids are the demand for energy, and the generation of energy, and if applicable, it must balance purchases and/or sales with the utility linked to the smart grids. Marginal costs indicate the price of energy for each period. The approach can be conceived as an artificial brain composed of a network of mathematical models, a model for each smart grid and for each site of large generation and/or consumption. Communication between the algorithms of mathematical problems must be asynchronous when events occur in the system. This can be continuous. For optimization purposes, the artificial brain does not need a coordinator, as the smart grid system acts autonomously and independently. GSDDP, Generalized Stochastic Dual Dynamic Programming. GSDDP is a methodology developed by HI that has been mainly used in the high-power system. This system will be used to present GSDDP characteristics. The article, GSDDP and Risk Management, Theory and Supply Chain Design, presents detailed information about this case. In the future, the real-life problem solution based on mathematical programming, applied to large physical and social structures/organizations, must be based on multi-level parallelism using the modern computational architectures. Then, large-scale optimization methodologies are the way to atomize an optimization mathematical problem in multiple types of subproblems that can be solved using the concepts of asynchronous parallel optimization and real-time distributed optimization. High power may use methodologies like Bender's theory, Lagrangian relaxation, Dantzig-Wolff decomposition, column generation, disjunctive programming and its variations. These methodologies may be combined using cross-decomposition concepts to implement parallel and/or distributed optimization. To speed up the solution time of large-scale problems, HI created the algorithm GDDP, Generalized Dual Dynamic Programming. GDDP is oriented to solve dynamic optimization problems, integrating the Bender's theory and dynamic programming approaches. Based on the dynamic programming approach, GDDP makes a distinction between state variables and control variables. This distinction permits a more detailed algorithm in which the subproblems are smaller than in the algorithm's nested Bender's decomposition, NBD, widely used in the economic dispatch of power systems. The main limitation of NB, including dual dynamic programming, DDP, is that they only solve linear models. Then GDDP is more robust than NBD. As you see in the table. The table presents a benchmark, realized by High, between standard GSTDP and standard SNBD, stochastic nested Bender's decomposition, like STDP, using a stochastic linear economic electricity dispatch. The experiments show that the low complexity of the case does not always justify the large-scale methodologies. The best GSTDP option is, approximately, 100 times faster than SNBD, and the best GSTDP with NBD coordinator is, approximately, 15 times faster than SNBD. The following table and image resume the study of behavior of GSTDP for a stochastic mixed linear economic electricity dispatch. The decrease in the solution time per scenario, when increase the number of scenarios, is a measure of the learning capacity of the GSTDP. The third foundation of mathematical modeling in high power is large-scale optimization methodologies. In the field of mathematical optimization, stochastic programming, SP, is a framework for modeling optimization problems that involve uncertainty. The most used method is scenario-based SP, also known as non-anticipative stochastic programming. In this case, SP considers multiple scenarios, associating each of them with a probability of occurrence, and the model determines the best decision before the occurrence of the scenario, non-anticipative decisions. In OpTeX, the first step in implementing stochastic programming is to select the deterministic model that you want to convert to stochastic. The second step is to parameterize the uncertainty environment that converts the deterministic model into a stochastic one. Main aspect are: decision tree indicates how the model makes decisions. Stochastic process, the uncertainty dimensions must be defined by the users, considering which is the more real stochastic process. Risk management, the biggest advantage of stochastic models is the inclusion of risk measures in the stochastic model. Nowadays, the risk measure most used is the conditional value at risk, CVAR. Solution process, the solution approach of the model is an important point to consider. There are multiple alternatives. The selection is typical of experts in highly complex mathematical modeling. Below is the definition of a stochastic optimization model in OpTeX. The first step in formulating a stochastic optimization model is to define the uncertainty dimensions, and the index with which they will be handled. The screenshot presents the definition of a multi-stage decision tree. It is defined. The decision tree code and its description, non-anticipative variables, and the stochastic parameters, together with the indices of the uncertainty dimension to which they belong. The next step is to define the connectivity of the nodes and branches of the decision tree, including the probability of each node. The fields associated with the uncertainty dimensions must be included and filled in the tables of the industrial database. The last two steps are: link the model to the decision tree, and define the CVAR risk constraint. That's all. Non-anticipative constraints declaration. To ensure the consistency of the solution, so-called non-anticipative variables must be introduced, which are independent of the uncertainty dimensions, in blue, and must comply with anticipation constraints to guarantee the same value for a set of nodes according to the dynamic tree that simulates the stochastic process. In this example, taken from a stochastic expansion model of an industrial system, we have two non-anticipatory constraints associated with decisions on the operation of two industrial facilities, packing plants and distribution centers, in green. Non-anticipative constraints formulation. This constraint guarantees that the values of the non-anticipative variables are the same, for all internal scenarios belonging to a given set. Those interested in learning more about the implementation of stochastic optimization models in OpTeX may consult OpTeX Mathematical Modeler's Manual. Making Stochastic Programming Models Filling the Blanks. Industry 6.0. Stochastic Optimization. It can be said that the approach presented corresponds to a version of Industry 4.0, and that the change experienced until Industry 6.0 is very large, having affected the way of implementing mathematics, which is different from having changed mathematics. However, one of the most impactful changes occurs with the arrival of the Internet of Things, IoT, typical of Industry 4.0, which began to change the models that ran at discrete frequencies, such as days, weeks, months, for real-time models, which are the ones that should be used today. Autonomous Lagrangian relaxation. Consensus algorithms. Autonomous Lagrangian relaxation theory. LR is about solving the monolithic problem using large-scale optimization methodologies. Although the solution process may be parallel, the problem remains integrated and requires a coordination problem. ALR is about using a consensus algorithm so that each problem is solved independently, and the solution is obtained through a consensus among the players participating in the game. The rules of consensus are based on the Lagrange theory. There is no monolithic problem, there are n independent problems. To determine optimality, the advanced metering infrastructure, AMI, of all electric systems must match. To do this, each electric system knows all the AMIs and moves towards the Lagrange multiplier solution. The electric systems will move autonomously, following logical rules that guarantee convergence, for example, moving towards the average of the Lagrange multipliers. For static processes, this consensus rule ensures that the problem will be optimal. Considering that LR is a primal non-feasible method, to use its results at any time, it is necessary to implement a mathematical problem that recovers the primal feasibility. In this case, it is a matter of recovering the feasibility of the demand and the generation equations. The feasibility recovery problem can be independent and reside in the AMI. To do this, it is necessary to implement an empirical rule of consensus based on optimization. The evolution of Lagrangian relaxation, LR, in Industry 6.0 has been named by High as autonomous Lagrangian relaxation, ALR. ALR is based the mathematical principles of Lagrange theory but is aimed at modeling living intelligent systems, which are autonomous and do not require coordination problems. On the other hand, its greatest strength is the modeling of systems in real time, based on intelligent sensors. ALR can also be called distributed Lagrangian relaxation, DLR. To differentiate itself from distributed Lagrangian relaxation, DLR, Lagrangian relaxation can be called centralized Lagrangian relaxation, CLR, since the model remains monolithic, and is solved in parallel using large-scale optimization technologies. The approach can be conceived as an artificial brain composed of a network of mathematical models, a model for each component of the system. The communication between the algorithms of mathematical problems can be asynchronous. It occurs when events occur in the system. This can be almost continuous depending on the speed of the AMI. For optimization purposes, the artificial brain does not need a coordinator, as each component of the system acts autonomously and independently. The consensus rules are based on Lagrange's theory, which must satisfy all problems. Each problem receives information from the AMI, and if it is far from the mean of the marginal cost, it moves towards it. Consensus algorithms. Consensus algorithms are fundamental to the operation of decentralized networks, mainly blockchain networks. They ensure that all network participants agree on the validity of transactions and the state of the blockchain. Without consensus, there would be discrepancies in the data between different nodes, which could lead to fraud and errors. These algorithms facilitate trust between users who may not know or trust each other, allowing decentralized systems to function effectively. Different consensus mechanisms have been developed to respond to the needs of various applications, each with its own strengths and weaknesses. Validate transactions and add them to the database. Prevent double spending and fraudulent activities. Improve network security against attacks. Optimize network performance. Allow decentralized decision-making. The importance of consensus algorithms cannot be underestimated, as they provide the backbone for the reliability of autonomous and distributed networks. They ensure that all participants maintain a unified view of the network, which is essential for transparency and accountability. These algorithms protect the network from various types of attacks, such as Sybil attacks, where a malicious actor creates multiple identities to take control of the network. The choice of algorithm can significantly affect the speed and scalability of transactions. Therefore, selecting the right consensus mechanism is a critical factor in the design of a decentralized system, because they establish a safe and reliable way to reach an agreement, minimize the risk of network forks, which can lead to confusion, allow the system to function without a central authority, dictate how quickly transactions can be processed, and influence the costs associated with maintaining the network. As George Bernard Shaw would say, imagination is the beginning of creation. You imagine what you desire, you will what you imagine, and at last you create what you will. Hyde tries to have the capacity of Bernard Shaw's imagination. Thank you very much for your attention.